This is day 3 of our waves unit. Today we'll be discussing new ideas like frequency and period, and using them to calculate the speed of a wave. You may remember in our previous lesson, I talked about how in order to change the speed of a wave, we need to change its medium. You can see here, gas, liquid, and solids are each different mediums. Uh, Solids have particles that are packed close together as opposed to liquids and gases. And energy is transferred through collisions between particles. So you'll see that solids are going to pass energy along more efficiently. So the wave will happen much quicker as opposed to liquids and gases. But today's about cycles and frequency and period. Remember that a cycle is one complete repetition of a periodic wave. So really what we're looking for is an entire crest and an entire trough in a cycle. The period is the amount of time it takes for an entire crest or entire trough to pass through a position in space. Period is marked by capital T, and its unit would be seconds or time. And frequency is the reciprocal of period. If this is the amount of time it takes to complete one cycle, period, frequency would be the amount of cycles you could complete in 1 second. So frequency is lowercase f, and its unit is 1 over s, as you can see here, 1 over period, 1 over s. Or we say hertz. They are reciprocals of each other. So let's use that idea to help us determine um, like the period and frequency of a stagnant graph here. So this is a graph that represents a displacement of a point and a medium as a function of time. So let's say it's a cork on an ocean and the waves are moving through it, and the cork is going to be displaced upward to the full amplitude and then downward all the way to the bottom as the wave moves to the left and then back to its original position. So it'll have gone through an entire cycle in a half second, 0.5 seconds. So what is the period? Well, that is exactly the period. It's the amount of time it takes to go through an entire cycle, to go all the way up over the crest and all the way down through the trough and back to the original position. That is 0.5 seconds. The frequency is 1 over 0.5 seconds. So that would be basically how many times can you do this in 1 second. So it's 1 divided by the period. 1 divided by 0.5 is you could do this twice in a second. And that's exactly what we have happening here. 1, 2 times in a second. Very simple idea, period and frequency. Let's see this in action in a more dynamic setting. I want to pull out an old flash of mine that Mr. Belling put together. It's called a smiley face inner tube guy. And he is going to ride on a wave in his little inner tube. And as he reaches the top, you can hear a noise to mark that he's there. And I'm going to use that to manually time his period, right? Because each time he reaches the same position, he's gone through 1 complete cycle. The amount of time for that is period. So let's figure out his period the next time he reaches the top. I'll start, and I'll stop at the next time. All right. It looks like this period is about 3 seconds long, about 3 seconds. So let me pull out my my paper, and I'll mark that his period is about 3.1 seconds long, right? That's his period. I'll pull that down. And if I want to figure out what the frequency is, I have to remember that period is 1 over f, and the reciprocal of that is right there. So frequency then, if I want to know how many times he could do this in a second, it's not going to be very many times. In fact, it's going to be a fraction of the time. So it's 1 over 3.1. He's only going to get a little bit of his cycle in. It's somewhere, you know the number, it's like somewhere around 0.3. So it's 0.32. 1 over S is our unit, or hertz, 0.32 hertz. All right. So we're actually manually timing Smiley interface tube guy, and then we're going to figure out the frequency using our formulas. Let's do it again here, and this time I'll have you pull out your timers. Let's pause the videos so everybody can pull out their timers. All right, now that you have your timers, let's start them up. All right, that looks like it's about 1.48 seconds. 1.48 seconds. Let me pull out my drawing pad. If I want to figure out the frequency here, it is 1 over t, which is 1 over 1.48 seconds. And my calculator, 1 divided by 1.48 is going to be 0.68 1 over s, or 0.68 hertz. It's important for us to remember and understand, I guess, that cycles does not get a unit. So this is the number of cycles in 1 second. Cycle doesn't get a unit, so it just remains a 1 over here. So 0.68 hertz is the frequency of Smiley face inner tube guy. Now let's take a brief look at what's happening here. As the period gets smaller, because we're dealing with reciprocals, the frequency is going to increase, and vice versa. So very interesting. Let's go back to our slide deck and take a peek at what we have next. This is speed. We're going to be calculating speed now. The speed of a wave is a product of frequency times wavelength. All right, so this is basically what that statement is saying. V equals frequency times wavelength. But how do we get that? Well, we know that speed or velocity from kinematics is distance divided by time, or displacement divided by time. And the very distance of speed the energy travels is a wavelength. So distance is going to be wavelength, and time is going to be the period it takes for a wavelength to move in an entire cycle. So V equals lambda divided by t, distance divided by time. And since we know this, that period equals 1 over f, this is really lambda over 1 over f, right? If we substitute the 1 over f for this business here, well, if I cross multiply the numerator times the denominator, I would end up with frequency times wavelength. You have all of these formulas available to you. This chunk here, this chunk here, and this chunk here. We can use them all. So here's a problem that is pretty straightforward. We have a few waves moving through a medium, a few pulses, and it looks like the section of medium that we're interested in is 6 meters long, and we happen to have, let's see, how many waves do we have? We have 1, 2, 3 waves in this medium. So that's 3 cycles of wave in this medium. So let's write 3 cycles in our medium, and we don't know what the wavelength is. So that's going to be 6 meters divided by 3 cycles is 3 meters. Our wavelength is going to be 6 meters divided by 3 cycles is 3 meters. So what is the period if it takes 6 seconds to travel between position A and position B? For a crest to go from A to B, well, that looks like it's the length of an entire wave anyway. So it's going to be the amount of time it takes one cycle to happen, right? So the period is 6 seconds. The amount of time it takes to go an entire crest, an entire trough, is going to be the period, and that is 6 seconds. So what is the frequency? The frequency is 1 over 6 seconds, which I believe is 0.13. 1 divided by 6, oh, 1/7. I'm not really good at math. It's 1 over s, or hertz. So that is our frequency of this wave. Next, we might also come across some problems where we need to determine, I don't know, the speed or the wavelength when you're given a frequency, or maybe it isn't obvious what the speed is, but our reference tables tells us certain speeds. Like there are constant speeds. The speed of light in a vacuum, like in space between planets, would be 30 million meters per second. It gets a special letter C. So this is a constant on the front page of our reference table. We also have another constant, the speed of sound in air at standard temperature and pressure. That is 331 meters per second. Now we say standard temperature and pressure because different positions in our atmosphere, we have different pressures, we have different temperatures, and each of those, from our very first slide today, you know that density affects the rate at which we'll transfer energy because there'll be either more or less collisions, right? So where it's more dense, we would have more collisions and therefore a faster rate of speed. At standard temperature and pressure, this is our speed. So our problem here today says the middle C note on a piano vibrates at precisely 261.626 hertz. What would middle C's wavelength be at STP? I'm going to show you what that is. This is an online tone generator, and I have it set for middle C. This is what it sounds like. That is 261.626. And we'll use our drawing pad to figure out what the wavelength of middle C would be in our room where the piano is being played. So what are we dealing with here? We have wavelength is what I want. What is the wavelength of middle C? I have the frequency of middle C, 261.626. And I know the speed of middle C is not given to me in the problem, but I can look it up on the reference table. It is 331 times 10 to the second, or 3.31 times 10 to the second meters per second. So what are we doing here? We know that velocity equals frequency times wavelength from our formula before. You're probably thinking this is annoying, so I'll turn it off. Let's solve for wavelength. Wavelength equals frequency divided by, velocity divided by frequency. And this is going to be 331 meters per second divided by 260, let's call it 2, 1 over s. So when we do this work, we're going to find out that it is actually a little bit longer than a meter. So literally, it's 1.26 meters. The wavelength of middle C is 1.26 meters. You know what a meter is? It's about a yard. This is almost a yard and a third, maybe about 4 feet in length. Between these are going to be longitudinal waves. So between compressions in the space surrounding the piano, we would have about 4 feet between compressions at standard temperature and pressure. That's pretty wild. Very good. So today, I'd like you to work on the supplemental notes and problems that I've assigned you, and have a good day.